Okay, so just want to talk through these need to knows for a moment. It says that momentum is conserved in an isolating system, so your total momentum before equals the total momentum after. What that is going to mean is that the change in objects, one object's momentum is the change in the other object's momentum. So what one it loses, one gains, because it's transferred from one to the other, and none of it disappeared or appeared, so whatever the amount that this one loses is the amount this one gains. Isolated means there's no external or outside forces. There can still be an internal force, so that could be like, when we talk about somebody throwing a ball, the force of the hand on the ball and the ball in the hand, that's still inside the system of the person in the ball, or with the spring is acting equally on both objects, that's an internal force, etc. Outside force would be like a hand coming in and doing something with two cards or friction, etc. In an elastic collision, kinetic energy is conserved. Inelastic, kinetic energy is not conserved. When they stick together, that will always be inelastic. When they stick together, you're going to lose kinetic energy. Another example of inelastic is whenever they jump apart, so those explosion ones. In that case, kinetic energy is not conserved, you're gaining kinetic energy. And in a collision, momentum should be conserved. That is doesn't matter what type of collision, momentum is conserved, also in the explosion questions, unless there is an outside or external force. So, in the collision, the two objects should have the same change in momentum because the total stayed the same, it's just transferred from one to the other. Their impulse should be the same because the impulse is change in momentum. They should feel the same force because if it's an internal force, it is literally one force on the other person and the other one back on it. So it's the same force, A and B and B on A. And they'll have different accelerations and different changes in velocities because acceleration will be F over M and change of velocity will be delta P over M. So if these two things are the same but they have different masses, then they'll have different accelerations and change of velocities. Impulse, that's just change in momentum. So you can use that change in momentum is just F delta T. And if we're looking at the graph of a force time graph, that means you're going to calculate the area because you're multiplying the force times the time. And then in a collision, the center of mass velocity will be the same unless there's an outside force. And just be super, super, super careful with your signs. A lot of you have gotten lots of points off just because you forgot to put a negative for something moving left. But for energy, remember energy, even if I plug in negative V, it's getting squared, so see how the negative sign goes away? So I'm not worried about energy because energy doesn't have direction, but momentum does. P equals mv, change of P is F delta T, these are on our equation sheet, and then we also should know the relationship delta P is M delta V, that's worth it to know. All right, first one, we've got 2 going to the right at 5. I'm going to put 0.25 going left, so negative 10. And it says they stick together, so we've got 2 and 0.25. I want the kinetic energy after, so kinetic energy after is just going to be 1/2. This is just the same as 2.25, but I need to find that velocity first, so I'm going to use momentum to find it. Momentum before equals momentum after. This right here is 7.5. Make sure you have that negative sign. Divide over, you get velocity is 3.33. That's the final velocity. And that's the velocity I need in order to calculate the kinetic energy afterwards. Put that in your calculator, you get 12.5. Number 2, we've got force in time. We've got the mass right here, and we've got that the initial velocity is -8, and we want V final. So anytime you see a force time graph, you should think this, I need to find the area. So this is a triangle, base times height over 2. One thing to be careful with is this is in milliseconds, so this isn't just 3, this is 3 times 10 to the -3. And you don't have to memorize that, right? Milli is on the equation sheet. If you just go to the back and find M for milli, it'll say times 10 to the -3. So the base is 3 with the milli. Height is 6 divided by 2, this gives me 0.009. That's my area, the area of force time graph. You're multiplying force times time, so that's going to give me change in momentum. Now, I'm talking about velocity, so I'm going to use my change in momentum as m delta v equation. Change in momentum is 0.009, mass is 0.001. Divide over, you get 9. Now, change in velocity, I just think of it as I start with -8. If I change by +9, that means I added 9, so now I'm at +1. But you can do the delta v is v final minus v initial. 9 equals v final minus -8, which becomes +8. Subtract over, you get the same thing. I will say that this, I feel like you're less likely to make mistakes if you just know that it's initial plus the change. And it will always be plus, because if you have a negative change, then it'll be just plus that negative. So you just add the change to the initial to get the final. Two particles collide, don't really know what was happening, but now they stick together. Which of the following is correct for the total momentum, the change in total momentum, and the change in total kinetic energy? This is a collision, so the total momentum should be conserved. So the total change should be 0. Now the change of this guy doesn't have to be 0, it has to be equal to the change in this guy, right? But the change in the total should be 0 because it stays the same. Now in a collision, it is not guaranteed that your kinetic energy is conserved, right? In fact, most collisions you're gonna not have it conserved. So this is the stick together case. This is an example of an inelastic collision. Anytime they stick together, you lose kinetic energy. So if I'm losing kinetic energy, the change in kinetics should be a negative change. Kid riding in a wagon with a ball. Whole system is moving at v. Afterwards, the ball goes out at 2v. The kid is probably going slower. I'm looking for the velocity of the center of mass of the kid wagon ball system. So let's think about, we know the rule that the velocity of the center of mass stays the same unless there's an outside force. This one, the only force is him on the ball and the ball back on him. So that's not an outside force, that's internal between the two objects. So then that means that the center of mass velocity should be staying the same. So let's think about all of them together had a velocity of v. So then the center of mass had to have been traveling v because everything was. So then the center of mass velocity is just v, and it stayed like that, so it's still v. Right? It doesn't really matter what this velocity is or what this velocity is, who's heavier, etc. It's the same as before, and before everything was at v, so the center of mass had to be at v. We are looking at 5 coming into some stationary car, and then they stick together and go up with some velocity. I'm looking at the velocity graph of this, of the cart, or no, sorry, of the block coming in. So I see how I'm starting at 4 and going down to 1. Here I'm starting at 4 going to 3. I'm starting at 4 and going down to 2. So I know that no matter what, right, picking up any mass, I'm going to slow down in this collision because it will transfer some of its momentum to this guy when they stick together. But I won't necessarily transfer like a lot of it, right? So if I'm transferring, if I'm hitting a really, really big object, a heavy mass, you're going to be giving most of your momentum away, so more than half of it. If I hit a mass that is exactly my mass, then I'm going to give exactly half away. And if I hit a mass that is smaller than me, then I'm going to give less than half away. So I'll only slow down a little bit. So I look at the first case, going from 4 to 1, this slows a lot, right? Give away more than half. Here, I only slow a little bit. And then here, I slow to exactly 1/2 the initial velocity. So that means I've exactly halved my momentum because I hit somebody the same size as me. So C. This one, I slow down only a little bit, so I gave away less than half. I must have hit something less than me. And here, I gave away more than half. I must have hit something more than me. Number 8, object X travels with the speed of 3. And 2 is initially at rest. And they stick together. And I want to know how much mechanical energy is converted into non-mechanical energy. So mechanical energy is like the total, right? We're thinking about both potential and kinetic. It doesn't say anything about it being on like a ramp or anything, so I'm going to assume that there's no change in potential. We're just talking about kinetic here. And I'm asking how much of that kinetic energy is converted into non-mechanical or basically like lost. Obviously you can't totally disappear. It goes into some energy that we don't talk about, right? So like heat energy or sound or something like that. So I want to know how much energy is lost. I need kinetic before and I need kinetic after. Kinetic before is just 1/2 mass of 4, 3 squared. Plug that in your calculator, you get 18. To find kinetic energy after, I need to know the velocity after. I'm going to have to use conservation of momentum. So you get velocity of 2, and then my kinetic energy after is 1/2. I treat this as a mass of 6 because it's all stuck together, 2 squared, so then this is 12. So if I started with 18 joules and I end with 12 joules, see how I lost 6 joules? That's how much energy was converted into non-mechanical energy. We've got 4m coming in at 5 V-naught, and m is at rest. It says block X collides elastically with block Y. Block X has a speed of 3 V-naught in the same direction as before, so the 4m is now at 3 V. And what is the speed of m after? So I'm going to call this V2. Careful when we were working on this, a lot of people just made them stuck together. Don't have them stick together unless it specifically says they stuck together. Collision, we're going to use conservation momentum, so 4m 5 V-naught equals 4m 3 V-naught plus mv2. Now I had the question a lot, can the 4m's cancel out? In this case, the 4m's cannot cancel out because I have 3 terms, and 4m is only in the first 2. See how this term right here doesn't have one? So I can't do that, so I'm going to kind of simplify this. 4m and 5 V become 20 mv. This becomes 12 mv. Then I can subtract, I'm trying to get this by itself, so I subtract this term over. And I can cancel out an m, so your answer is 8 V-naught. Here the graph shows the position of the center of mass as a function of time. So this is position measured in seconds, and this is time, oh sorry, that's definitely measured in meters, and that's measured in seconds. My bad, I meant to label this before I printed it. I've got a mass, and at t equals 2, there's some external force, and I want to know the change in momentum of the system. 2 ways to find change in momentum. First is F delta t, and the other one is the m delta v. We often, talking about a graph, use this one because I'm given a force time graph, but that's not what I have here. I don't have anything that will help me find the force, so I'm going to say no to that. I'm going to use this one right here. So I need m, and I need v final and v initial. Mass I know it's 2. I need to find the 2 velocities. So see how we have a velocity right here, and then we have a new velocity? To get the velocity from a position versus time graph, remember we want to get meters per second, so I'm going to take the meters and divide by seconds, so that's just the slope. So in the first section, see how you go up 2 and over 2? 2 meters in 2 seconds. This has a velocity of 1. And then here, I'm going from 2 to 5, so that's going up 3 meters. 2 to 3 seconds is 1 second, so then this is a velocity of 3. So my initial velocity is 1, final velocity of 3, change of velocity is 2, times mass is 2, is a change in momentum of 4. 2 blocks of mass m and 3m move towards each other with the speed v. They collide and stick together, which shows the momentum of 3 before and after. So let's make these stick together. They're both coming in with the same velocity, but the 3m obviously has more mass, so it has more momentum. So when they stick together, they're going to be traveling to the left. I know that the 3m came in with v, but when it hits the m, it's going to give some of its momentum to this guy so that it can turn around. So I know that this is negative, but it's slower than the original v, because the 3m will be giving some of its momentum away. So I need to start negative, and I need to go to negative, but slower. So I can cross off a and b because they don't end negative. C and D both start negative and end negative, but I need to be getting slower. So think about here I have -2 to -1, and here I have -2 down to -4. 2 meters per second going to 4 meters per second is getting faster, so -2 going to -1 is getting slower. I get that this one actually goes up, but remember you're going in the negative going up is actually getting closer to 0, so I got slower here. 3 balls, all with equal masses, are free to move. Ball B is at rest. A and C are both moving with the same speed, so all have the same mass. This guy's at rest, this one's V, this one's coming in at -V. That's my before picture, and then afterwards it says that A and B stick together, and C bounces off, so C is now going to be going off to the right, and I want to know that these two, when they stick together, I want to know what direction did they go. So we're going to use conservation of momentum, because this is definitely a collision. Think about the total momentum at the beginning, right? I had one positive and one negative equal amounts, so this is going to cancel out to a total momentum of 0. Total momentum must be conserved, so I still need a total momentum of 0. So if C is going to the right and A and B are stuck together, they have to be going to the left, so that momentum can still be conserved, can still cancel out to 0. All right, a car on a freeway collides with a mosquito that was initially at rest. I think it confused people because mosquito is super, super small and is like basically the negligible case. So let's say that this is actually, let's do like a, don't want to say another living animal because that would be bad. So maybe it hits a trash can. Okay, a big trash can in the middle of the road. The total momentum of the system should stay the same, right? Total momentum should be conserved in a collision. The momentum of the trash can, well, at first it was at rest and then it's going to start moving, so it must have increased. The momentum of the car, well, the car, when it hits it, is going to slow down a little, right? The car had to give some of its momentum to the trash can, so that would decrease, right? One should always increase, one should decrease, so that the, right, one loses, one gains, because it's just transferred. The change in speed does not have to be the same. Remember, change in P is m delta v. We know that they are going to have the same change in momentum because it's transferred. So if I divide m over to get the change in velocity, the one with the smaller mass will have the greater change in velocity because this is an indirect relationship. So who had a greater change in its speed, that's the one with the less mass, which would be the trash can. Which changed its momentum by more? Same amount, because the total is conserved, so total P is conserved. So it's just the car transferring momentum to the trash can. So if it's just transferring, right, however much this one gives is how much this one gets. And then there are those of you who are like, wait, but the car is like way heavier. And I get that, but think about change in momentum is m delta v. The car does have a much greater mass, but it's not going to change its velocity very much. And the opposite is the trash can doesn't have very much mass, but is changing its velocity by a lot more. Balances out to the same. Greater impulse. Impulse literally is change in momentum, and we just said they have the same change in momentum, so they have the same impulse. And who feels a greater magnitude of the net force? So think about the only force that the car feels is the force of the trash can hitting it, and the only force that the trash can feels is the force of the car hitting it. So it's literally the force of the trash can and the car on the trash can. That has to be the same force. 5 kilogram toy car rolls down the ramp. They started from rest at a height of 0.8. And this is 5. And then they are going to come in and stick together. The other car has mass of 3 kilograms. And they stick together, and I want to know this velocity. So the first part, I'm changing from potential to kinetic, so that's going to be conservation of energy. Potential goes to kinetic. Here, this is a collision. I'm going to use conservation of momentum. But first, I need to find this velocity using change in energy, or I guess conservation. So mgh is 1/2 mv squared. You can plug in the 5, but I just like to save time, so cross off the m. So this is 10 times 0.8 equals 1/2 v squared. Multiply the 2 up, and you get 16 as v squared. Take the square root, velocity is 4. So this is coming out with a velocity of 4, which means it's coming towards the 3 with a velocity of 4. So now I use momentum. Momentum before equals momentum after. That's the same as like an 8v. So this is 20 is 8v. Divide over 2.5, I think. Hope so. Number 15, it says these two are going to come in and stick together. How much mechanical energy is transformed into internal energy? So this is again like this mechanical energy is going to be lost. The internal just means like when the things hit, they like, I don't know how to explain internal energy. It's basically like not potential or kinetic that's like in the system. Anyway, basically you can translate this to how much energy is lost, so how much kinetic is lost. So let's find kinetic before. So this is 1/2 3mv squared plus 1/2 m. Technically this is negative v, but you do not want to put the negative sign right here.